Well, good morning. Happy off-campus learning day. We're going to continue our lesson on the second fundamental theorem of calculus. You have your handout, and we had finished page 1 with our accumulator function. We found the derivative, capital F prime of x is equal to 2x. And we summarized that on page 3 with a statement that looks trivial. Capital F prime of x equals lowercase f of x. That's true only when you happen to have a constant as your lower limit of integration and x as your upper limit. These can actually get a lot more complicated. So let's take a look at page 2 of the handout. Now, up top, just a verbal review, an indefinite integral is an antiderivative. A definite integral can be thought of as a limit of a Riemann sum or it can also be thought of as a net accumulation of a rate of change. A net accumulation of a rate of change. Just like velocity is a rate of change in position. And the third way to think of a definite integral is a net accumulation of signed area. Net accumulation of signed area. So we add up all of the positive area, the negative area, which essentially gives us another way to think of it, and that is net change. You're taking the definite integral of velocity, that will give you a net change in position. Definite integral of velocity is net change in position. It's final position minus initial position. So there's many different ways to think of a definite integral. Now, we're going to sketch the graph of capital G of x. G of x is an accumulator function. Notice what's happening in the real world here. Let's make a real world connection. Snow is falling at a rate of sine t inches per hour. That's the rate of change in snow. Now, sine, let's take a look at your sine function. Sometimes it goes negative. So here's a situation where it's not only snowfall, but also snow melt. It's like we're snowing. From our birthday cake example, we expect it to accumulate 2 inches of snow and then to melt 2 inches of snow. Let's see if that plays out. So g of 0 has got to be 0 because the definite integral from 0 to 0 is the input of anything is going to be 0. And the sketches I'd like you to look at are, by the way, the parent graph we'll put right here for sine x. Here's the rate of snowfall. This is the t-axis. And the f of t, that's a lowercase f of t axis. The sine graph goes maximum at pi over 2, minimum at 3 pi over 2, back to a mid at 2 pi. So here's the rate of snowfall. It goes up to a maximum of 1 inch per hour. At time pi o'clock, we're down to 0 inches per hour, after which, by the time we get to 3 pi o'clock, snow is melting at a rate of 1 inch per hour, and at 2 pi o'clock, snow is neither accumulating nor melting. So g of 0 is 0. G of pi over 2 simply means the definite integral from 0 to pi over 2 of sine t dt. Now you can do the integral. The antiderivative of sine t is negative cosine t, and evaluate negative cosine t from t equals 0 to t equals pi over 2. And since the cosine of pi over 2 is 0, we get negative 0 minus negative, and the cosine of 0 is 1. So negative 0 minus negative 1 is just 1. So g of pi over 2, the amount of snow that's accumulated by the time we get to pi over 2 o'clock is 1. So let's have another sketch forming over here. Let's take a look at the graph of capital G of x on the vertical axis, and x here, let's plot the point 0, 0. And then by the time we get to time pi over 2 o'clock, we're up to 1 inch of snow on the ground. So by the time you get to pi, this is going to be the integral from 0 to pi. It's going to be negative cosine pi, or negative, cosine of pi is -1. So the opposite of -1 is 1 minus -1. It's got to be negative cosine t evaluated from t equals 0 to t equals pi. That's negative cosine pi minus negative cosine 0. So that's the opposite of -1 plus 1. 1 plus 1 is 2. So that makes sense. Remember, we said that the area under the sine curve is, well, on my daughter's birthday cake, I put the definite integral from 0 to pi over 2, which is 1. So it stands to reason that if you go from 0 to pi, that would be 2. And that's what we see here as we check it. And then g of 3 pi over 2, basically 2 inches of snow has accumulated and then 1 inch has melted. So by the time we get to 3 pi over 2 o'clock, we're down to 1 inch of snow. So if you do the work, that's going to be 1. By the time you get to 2 pi o'clock, all the snow that fell will have melted. And the graph is actually, it's sinusoidal in shape. That looks like it looks like a cosine function with a vertical shift of 1 and a vertical stretch factor of -1. I think that this is the graph of 1 minus cosine x, is what this orange graph looks like. And we could actually establish that by going back to the original expression and just using what we know about the first fundamental theorem of calculus. Let's take the antiderivative sine t, which I'm going to do here in green. I mean, here we arrived at an answer graphically, but I think we could have done this just using the first fundamental theorem of calculus. The antiderivative of sine t is negative cosine t, and if you evaluate that from from t equals 0 to t equals x, you get negative cosine of x minus negative cosine of 0. Simplified, you get negative cosine x plus the cosine of 0, which is 1. Sure enough, negative cosine x plus 1, that's the same thing as 1 minus cosine x. So this is a graph that has a maximum value at pi. And so in calculus, and on the AP test, it's not unusual to try to find the extrema of an accumulator function, to be able to find the maximum value of capital G of x. But we can tell graphically that the maximum value is at pi. By the time this lesson is over, we've got to be able to take any function and find any accumulator function, take its derivative for the purpose of finding extrema, local maxes and local mins. Now, that's fairly trivial when you have a situation in which the lower limit of integration is a constant and the upper limit of integration is x, because it's really just a matter of saying that g prime of x, according to the second fundamental theorem of calculus, g prime of x, not surprisingly, is just going to be sine of x. And when is g prime of x equal to 0? Well, sine x is equal to 0 at 0, pi, and 2 pi. So it's no surprise that the accumulator function has extrema, relative min, relative max at 0, pi, and 2 pi. That's trivial. But problem 2 is not trivial, because we don't have just plain x up here, we have a 5x. So now I'd like to show you how to find capital F prime of x when you have a non-trivial situation. So here we go. This is the heart of the lesson, And this is where we're looking at the level of difficulty that you're going to encounter on the Unit 4B test and on the AP test. So here we go. Here's what I recommend you do when you're trying to find capital F prime of X. First of all, show your work by writing the derivative with respect to X of this function. It's the derivative with respect to X of the definite integral from t equals 2 to t equals 5x of tangent cubed t dt. Now there's a routine that we can follow every time. And here's how you think about it. We're taking the derivative of what can be thought of as an antiderivative. I mean, yes, it is a definite integral, but there's definitely the antiderivative idea wrapped into the definite integral. So what I'd like you to do is leave the dx untouched, but the derivative, the d up here, wipes out the antiderivative. And so there are two d's that survive this epic battle. The derivative and the antiderivative clash. They wipe each other out, and when the dust settles, the dx survives and the dt survives. So after the epic battle, we have capital F prime of X equals tangent cubed of t has survived the battle. dt dx is still with us. And this has to be evaluated from t equals 2 to t equals 5x. Now, here's what you've never seen before. We have to evaluate an expression that contains not only t, but also dt dx. And so for every value of t, you need to come up with a companion value of dt dx. So I think that you'll remember to do that most easily if you always write an arrow here. Look, if t is equal to x, then dt dx, the corresponding value of dt dx would be 5. Where did I get that? I just took the derivative of both sides of this equation. The derivative with respect to x of t is dt dx, and the derivative with respect to x of 5x is 5. Likewise, if t is equal to 2, the corresponding value of dt dx is 0. Now I'm ready to actually evaluate this expression at these two limits. So, starting with the upper limit, it's going to be tangent cubed of t, which has a value of 5x, multiplied by dt dx, which is 5, minus, and now I'm going to have to put a value of 2 in for t, and this has gotten a little bit big. I'm going to shrink this down just a tad, so we have enough room for all of this. Okay, so it's tangent cubed of 5x times 5 minus, now do the same thing with t equals 2. Tangent cubed of 2 times 0. Now, there's going to be some problems where this isn't 2x, but maybe it's 2 sine x or something. So this is not always going to be a 0 here. But in this case, the problem simplifies to 5 tangent cubed of 5x. So that is the derivative of capital F. And we can set this equal to 0 to find critical numbers. But for now, let's just write that as capital F prime of x equals 5 times tangent cubed of 5x. So you can see, just by putting a 5 in front of the x, that made this problem a little more complicated than just that trivial statement we saw on page 3. Let's go to the next page. and try this with a truly intimidating problem where as long as you draw those two arrows and take the derivative for each arrow, it'll be pretty systematic. Let's try it. Let's find f prime of y. At this point, you might want to press pause and see if you can do it by yourself. Press pause if you want. But here's the solution to number 3. If the question is, what is f prime of y? Then the answer is, take the derivative with respect to whatever this letter is. Take the derivative with respect to, before it was x, this time it's y. Take d dy of the definite integral from, this is a value of u equals 3 sine y all the way up to u equals 2y of cosine squared u du. This is the point at which the epic battle commences. I'm going to use the red color from the palette to make this epic battle go. The derivative and the antiderivative symbol obliterate each other. The du and the dy survive. They're going to combine to become du dy. So my next move is to write f prime of y equals, well, cosine squared u, that survived the epic battle, cosine squared u of, times du dy. Du over dy evaluated from u equals 3 sine y to u equals 2y. Shrinking things down just a tad, and now it's time to draw the arrows. I need not only a value of u, but a value of du dy. So let's differentiate both sides of this equation with respect to y. Du dy equals 2. So please write du dy equals 2. If u is 2y, then du dy is 2. Then try this one on your own. If u is 3 sine y, then what would du dy be? Just differentiate with respect to y. Okay, I get 3 cosine y. So this also has gotten a little bit large. I think we can fix that. Maybe not. Okay, here we go. Close enough. Okay, so in red, I'm going to write down what I think the final answer is. Because now I think the final answer is apparent. The final answer is this expression evaluated at these two values. So it's going to be cosine squared of 2y, we're expecting it to be a function of y, it is, times 2 minus the cosine squared of 3 sine y is what I put in for u, and the value of du dy is 3 cosine of y. So in case you thought this lesson was going to be trivial, it's far from it. I don't expect that you'll get any of these problems correct unless you do this arrow routine right here so that you know what value of du dy goes along with u equals 2y and what value of du dy goes along with u equals 3 sine y. So just to be clear, not only did I replace u with 2y, but also du dy with 2. And then after the subtraction sign, not only did I replace u with 3 sine y, but I replaced the du dy with 3 cosine y. So you really need 4 values, or 4 expressions for substitution. All right, let's go to page 4 of this lesson, which is indeterminate forms. And actually, yeah, that's not part of this lesson. So we are in a position where you are now prepared to complete 2 homework assignments. I have them posted in the general resources. I put up the general resources topic. You'll see a semester 2 syllabus in there. So assignment 4.09, I think it says, and 4.10. Both of these have to do with the second fundamental theorem of calculus, and you know how to do both of these. But I don't want to overwhelm you with homework on these off-campus learning days. So here's the plan. I want you to have 4.09, have that turned in by 2 p.m. on Friday of this week. And then we're going to learn a new lesson on Friday, but 4.10, that's going to be an online submission. Both of these are online submissions. I want you to have this one turned in by 2 p.m. on Monday. Now you might be wondering, when is the assignment that we learn on Friday going to be due? Well, you'll just have to come to class on Friday to find out. But these are the due dates for the 2 assignments on the Fundamental Theorem of Calculus. So enjoy those, and we'll see you Friday. Have a good night.